The thing to think about with soil testing is analogy that I like to use is this is like looking at your bank statement, right? Bank statements also have all kinds of numbers and figures and percentages on them. But ultimately, there's just a couple things you're probably really paying attention to. And that's like how much money are in your 401k, how much money is in your checking account, how much money is in your savings account, did you get paid last month? Those are some of the things. And then looking at all the minutia maybe gets a little bit confusing. And so if we take that same mindset of trying to understand what's the important parts and what's the parts that aren't as important, I think soil testing can still be kind of useful and powerful. So let's try to make soil testing work for you and for your facility. So I have a backyard putting green because I'm a weirdo and I miss taking care of the grass because all I do now is like write about grass and give talks and like advise graduate students. And, I got into this same reason you got into this because you like, being outside, working and working and having, the nice looking grass. So I have this backyard putting green and I went through the same process and I have 2 degrees in soil science, so you'd think this would be a pretty simple process. But these are the same questions that I have that I'm sure you guys have. So I decided, maybe I want a soil sample. I want to know kind of what's going on in that soil from a chemical perspective, and we're only going to focus on the chemical side today. And so, okay, I'm going to go take a sample and send it off to a lab, right? Sounds simple. But then you think about all the questions you have. Like, all right, well, how deep should I go? How many samples do I need? How much soil do I have to actually send off to that lab? Does anybody know how much soil a lab actually uses to do a soil chemical test? It's about 1.5 grams of dry weight, right? So if you're going to send them a 5-gallon bucket of soil, no, they're just going to take a little scooper from the top and they're going to throw the rest of it out, okay? So if you're only going to do 1.5 grams, you got to make sure that you're doing a pretty representative area because you don't want to just take one soil because they're going to take that scoop. You really want to take several different samples, combine them together, mix them up as best you possibly can, and then so that's more representative to what the soil's like. Should I take the grass off or not? It's a question I get all the time. Well, what about the grass? That can make an impact. Well, it generally doesn't because when they take that soil, they're going to take that bucket you send them, they're going to take maybe like a scoop out of it, they're going to grind it up real nice, and there's a screen that's going to sieve off the grass. There's no need to sit there and worry about taking the grass off or anything. Just take the cores, stick them in a bag, and send it off to the lab, and then they'll kind of homogenize it and go from there. Then you go, what lab should I use? I mean, in Nebraska, we have a bunch of really good labs. A lot of national labs are right in Lincoln or just outside of Lincoln. So how do I pick one over the other? Well, you look at price, you look at, are they accredited lab? You figure out what tests are they using, and we'll talk about that in a little bit. And then you look at the price tag and you go, wow, is it really worth all this cost, all this time? And, I got to go to the UPS store and send this stuff off, right? It's all these kind of hassles. Is it really worth it? Ultimately, though, I decide, yep, I'm going to go do it. So then I wait, and sometimes it can be wait a couple days, and if it's in the middle of the big farm push and all the farmers are putting soil samples in, maybe you got to wait a couple weeks. And so that can be a problem sometimes. So you get your report back eventually, and then this is the same thoughts that I have, and I'm sure most of you have. The first thing you go is like, wow, look at this report. Like, how many numbers and graphs can you put onto one report to make you feel really dumb because you don't understand what every single one of those things means, right? And you start thinking, are these all even important? Is looking at my calcium to magnesium versus my calcium to potassium ratio an important thing to worry about? I'm worried, is my sulfate to nitrate ratio? Like, what the heck does that even mean? Right? And you don't know, so then you ask me, and I say, I don't know what it means. But it's on the report. Maybe it's not always there to scare you, but it also, it's adding value in the lab's eyes. Like, they can make graphs. So they're going to take the soil, and they're going to figure out how much nutrients are in the soil, and then they're just going to start saying, like, well, what can I give them to show a value? So, I could give them a calcium to magnesium ratio, because that's going to maybe they want to manage based on that. But if we don't know what that ratio means, it really is just a complete waste, and it really is unnecessary. And then you'll go to the spot where you'll see, whoa, I'm low in something, right? You're always looking. Where's that word low? And then you see, there's a low. Calcium is always low. Calcium is low, it seems like, right? Even if soil's made out of calcium, somehow calcium is low. Do you know there's never been a documented calcium deficiency in turf in the field? Ever. But every single soil test report, maybe not all of them, but most of them say calcium is medium to low. How is that possible? How is it possible that we are low on calcium if an academic has never been able to document it in the field? The only way we can make a calcium deficiency happen is to put it in hydroponic water, where the roots are growing in water, and then we don't put any calcium in that water. So then it actually gets red, and it gets stunted, and that's what calcium deficiency looks like. Calcium and magnesium, too, also have very similar functions in the plant, in cell walls. So you hear people talk about, oh, I put down calcium and I get these healthier cell walls. The calcium's got two charges on it. It holds on to two different negative charges in a cell wall, and that electrostatic, that magnetism type charge, helps to hold the wall together. Well, magnesium can also do that. There's some ability for the plant to say, okay, I don't have enough calcium, I can take up magnesium. And so that's one reason we don't even see these issues, because a lot of soils have calcium, magnesium, and so we don't really have a problem there. But you see that word low and you freak out, and so what do? You got to call somebody. So you call your salesman and you order a bunch of stuff. Even though your grass looks good, you are now concerned that it's low on something and you got to fix it, because maybe I can't see that grass is struggling, but it really is, and maybe if it gets some stress on it, it's just going to die. This is something that I was talking to Frank Rossi about yesterday. Soil fertility issues don't cause the grass to just die. It's not like a disease. It's not like if I don't have a fungicide down and I get walloped with Pythium blight or brown patches everywhere. If you have a deficiency like phosphorus, you put some phosphorus down and it just slowly recovers. It might look kind of bad. It's not going to die from it. And so first of all, take away that fear. Take that fear away. If your potassium levels you think are too low, the grass is not just going to die because it's out of calcium or potassium. Maybe it's not up to its full potential, but it's not going to die as a result of it. But anyways, we go out and we buy all these materials and we start blanket applying them over the entire field, even though we haven't even tested to see, did I see a response out of that nutrient? Another issue with soil testing is the most important nutrient isn't even on the report. And if it is on the report, don't even pay attention to it. And that's nitrogen. Nitrate, ammonium, they're not on the reports for two reasons. One, healthy growing grass takes up nitrogen immediately. So it's always going to say it's low. It's the most limiting nutrient in the system. Microbes want it, plants want it, your turf, your weeds, anything. They want nitrogen. So sometimes you'll hear people say, oh, you have high levels of nitrogen. That caused the grass to die. No. You flipped it around. The grass was dead from something else, and then it couldn't take up the fertilizer you applied, and then you had high nitrogen levels in the soil. So if your plant is healthy and it's functioning and it's growing in the middle of the growing season, it's going to be high. When else could it be low? Well, if the grass isn't growing. If it's dormant or if it's going dormant. So into the beginning of spring, it might be higher. It's going to be lowest in the summer, and then it's going to begin higher in the fall, especially if you're doing a lot of late fall fertility to try to extend your season. So you don't want to worry about that too much. The other problem, nitrogen, it changes a lot. It changes from day to day. So if it takes even a week to get a soil test report back, the number is probably different now than it was when you soil sampled. So you can't manage to it. Another issue that can be a problem with soil testing, the roots have to be functioning to take up the nutrients in the soil. If the roots aren't working right, then they can't take it up. Anybody guess here what's the deficiency on this plot? It's Kentucky bluegrass, high pH soil, warm, wet conditions. Iron, yep. This is a true iron deficiency. You put down nitrogen fertilizer onto this grass, what happens? It gets yellower. It's crazy. Why? Because that plant can't take up iron. Iron is used to make chlorophyll. If you put down nitrogen fertilizer, it still stimulates a growth surge, but now there's even less iron to make chlorophyll. So it gets even more diluted. It gets more yellow. So if I'm going to try to fix this situation, what do I have to do? I don't look at my soil tests. Why? Because the roots aren't working. It's like if you have a root disease and you're having wilt, it doesn't matter if you have water in the soil, the roots can't take up the water. You have a root dysfunction going on from the hot, warm, wet soils with the high pH, especially in the bluegrass. We start to see this deficiency start to show up. So if we're going to solve this, it's not going to be by putting down iron to the soil, not granular, not watering in. It has to be foliar iron. So these are foliar iron fertilization. where you can see the different colors of green here, and the higher the rate, the more of the response that we saw. Here's an example of my neighbor that has this same problem. He waters his lawn every single day. I drive up to the YMCA in our neighborhood, and I see his sprinklers running every day, and sure enough, where's the deficiencies start to show up? Irrigation head, irrigation head, irrigation head, irrigation head. Right? And then what does he do because it's yellow? He waters it more, because that's how you solve the problem in his eyes, right? Here's a golf course that has it really bad. That's where we did our research. So they're not really overwatering here, but again, high pH soils. There's plenty of iron in these soils. If you soil test for it, it will say it's high. The problem is the roots don't have the mechanisms to take the iron up in those higher pH soils. And so a lot of the micronutrients are really misleading because they depend on the plant's ability to gather them as much as are they in the soil or not. So if we're worried about a micronutrient deficiency like iron or manganese or boron or zinc, the best thing we can do is to go out and do some of these little, you apply to a small area. So I had this area, and I did different areas, different levels of iron fertilizer, different forms of fertilizer. There's different chelates out there. There's straight up iron sulfate heptahydrate, which is a granular stuff. You can dissolve it down. But then you have EDTA and DTPA and EDDHA and citrate and all these different chelating materials. And so we wanted to see, did any of those have a difference on the plant's ability to respond to the green color? So we tested a whole bunch of different types of citrate, EDDHA. This is like a really expensive chelate we don't see in turf. It's more in greenhouses. And we looked at the different responses, and we found that they all responded the same. Essentially, the more iron we put down, the greener the color. And it didn't matter which chelate we used. Why? Because the chelates work in the soil, but if the roots aren't functioning, it doesn't matter. It needed to be foliar uptake. And so then it didn't matter if it was a chelate or not. So let's get into the soil test for nutrients we do care about. And so those are things like phosphorus, potassium, calcium, magnesium, sulfur, boron, copper, iron, manganese. These are all soil elements that we can test for. And so this is some soil test report. I don't even know where this is from. I just Googled it. But I thought it was an easy way to kind of show the 3 different parts of a soil test. So when you get your report, you have to kind of know what is the area that's important and what is the area that's bullshit so that you can, let's focus on the important parts, okay? So there's 3 different parts of a soil test report. 1, the results, highlighted in red. We got the actual numbers, parts per million, pounds per acre. It's going to have some kind of value like that. Cation exchange capacity is also a result, pH, the organic matter percentage. These are all things that you put into a machine, and a machine gives a number. So you can tweak this a little bit, deciding like what kind of tests you're going to use, what kind of a chemical extractant you're going to use to try to extract the nutrients out of the soil, and we'll talk about that in a second. But then it goes into a machine, and the machine just counts. Okay, there's, in this situation, for every million parts there's of solution, there's 30 parts of phosphorus. It just counts them. Okay? So that's how that works. So you can't manipulate it very much. But then the question I'd have is, it says, in this test right here, it says my copper is at 1.5 part per million. Who thinks that's too low? Who has no idea? I hope most of your hands go up, right? Okay. So we need an interpretation to then turn those numbers into understanding, is that what the plant needs or not? Okay? And so that's in purple here. So that's where we say, according to this lab, 1.5 part per million copper is at the borderline of optimum. But where do they get that number from? How do they determine that? So we'll talk about that. And so there's a little bit of opinion in there, right? Because depending on how they determine it, one lab might have a different opinion than a different lab. And then we start, this is like the CNN version of it. Now it's opinions on top of opinions. This is like, I got numbers, hard numbers. And I got an opinion, and I got someone's opinion of an opinion. And that's the recommendations. This is saying, how do you got to fertilize now based on my opinion, which is based on the number that I got from a machine. Okay? So you can see how all of a sudden we're getting like more abstract as we're getting through this soil test report. So let's get back to basics, like the title said. Talk a little bit about fertility. Nutrients in the soil can be either labile or non-labile, and so that means it can be available or not available. And so what we want to do is assess the nutrients that are plant available in some form, and we're going to use a soil extraction to do that. We're also talking a little bit about nutrient movement and nutrient uptake. So we have all of our nutrients here that that are being supplied by the soil. Primary ones in turf, nitrogen, phosphorus, and potassium. Again, nitrogen we don't pay attention to because it's too transient and it's always at low levels when the grass is actively growing. So phosphorus and potassium. And then we have secondary nutrients, calcium, magnesium, sulfur. And then we have our micronutrients that we actually have really, really bad guidance for to tell you is it low, medium, or high for a lot of those nutrients. But of those nutrients, they have to be dissolved in the water for the plant to actually take them up. So sometimes you'll hear people talk about, well, it's in the soil, but it's not in the water. The plant can't get it, okay? So let's dive into that argument a little bit more. So we have non-labile nutrients. That means not plant-available nutrients. This is just, if you could say, count every single nutrient in the soil and see how much is there, what will that number be? So this is an example of like a sheet of clay. You have a mica clay. And in between those sheets of clay, you have a bunch of potassium. So feldspar, things like that, different clay minerals are made out of potassium. They're the actual part of the rock of the soil or of the mineral clay. So it's a little misleading if you would count all of these potassiums to figure out how much potassium is in the soil because that potassium is locked up. It's in jail. It can't go anywhere. It can't go feed the plant. So total nutrients is something we don't really measure for. Another form of nutrients, though, go to our labile form, and these are forms that can be available to the plant. So as you get to the outsides of these clays or these soil particles or these organic matter, we have negative charges, and so a lot of the positive charged cations, the calcium, potassium, magnesium, hydrogen, aluminum, all the positive charges can then bind to those negative charges. But the bind isn't super tight. It's not like it's a chemical bond. It's not like it's in jail like this side over here. And then we have what the plant actually sees. And so some labs will call this available. And other labs will call it a saturated paste or what's in the water or the soil solution. And this is what's actually floating around in the water. So you might think, okay, well, if this is what the plant actually can use, I want to only focus on this. But the problem is, if a plant, say, takes up potassium, it's an equilibrium between how much is floating around in the water and how much is bound to the cation exchange sites. So if you take up potassium, this one will say, oh, equilibrium is not equal anymore, and this potassium bounces off and it fills. So if I'm trying to think about this like, how quickly nutrients can move, it's very slow for the potassium in jail here to work its way to the outside of the soil. It happens. Doug Soldat at Wisconsin is showing actually it can happen in some of our top dressing sands a little bit more. And that's one reason we don't see a lot of potassium requirements for top dressing a lot, especially with sands that have high levels of potassium in the rock. But then for the most part, this is a very fast reaction. Potassium is taken up, potassium on the soil releases and replaces it. So the analogy I use is we go back to this bank analogy. So I keep talking about soil testing like a bank account. This is your 401k. It's there. It's your money. You're not touching it. You might touch it if you had an emergency, but for the most part, you're not going to really use that money. This is more of like a checking account. That money's there, but it's kind of theoretical, right? Like I have money in the bank, right? So if you need to use that money to, say, buy some stuff at the county fair, you got to go to the ATM and you got to go replenish your wallet and actually get cash. Okay, so if you look just at what's in your wallet, that's not a good representation of how much money you have, because if you have a bunch of money in your checking account, well, you can always just get that money and turn it into cash. And you can also have too much money in your checking account or in your wallet. What can you do? You go to the bank and you put it back to checking account. So that happens rapidly. So that's kind of what we're thinking about. If we're trying to figure out how rich we are, how much money we have right now to satisfy the needs of my family, then I'm going to look at what's in my wallet and what's in my checking account. I'm probably not going to focus on my 401k. Other nutrients, another nutrient that's important is phosphorus. And phosphorus has got a negative charge on it. So it doesn't just want to stick to the soil. It actually sticks with a much stronger chemical covalent bond. And so it's harder to extract. So if you wanted to look at how much phosphorus is in the soil, it's very, very, very low because it binds extremely tightly to the soil. It doesn't mean it's not available, though. If a plant takes up this phosphorus, a molecule, what happens? Well, one of these bonds can break and it can go back to replenish it. But it's just not like just easily floating around in the soil. I can't just wash it off really easily. We have to use acid or fluoride to try to chemically break it off the soil if we want to count it when we do our soil extractions. Let's see. Another thing to know is that plants have the control. You have little control of what gets in your plant. Okay? If that plant wants sulfur, it's going to turn on some of these specialized proteins on the outsides of the cells, on the outside of the roots, to take up sulfur. If it doesn't need sulfur, it doesn't matter if you put a whole bunch of sulfur down. Okay? So the plants are selective for their nutrients. We put something down, doesn't mean it's just going to get into the plant. So my analogy I'd use is if I go into, I'm watching sports on the weekend, right? And I go into my pantry and I want to just, binge on junk food, and I want like 2 Ho-Hos and a Kit Kat, right? The pantry is the soil. As long as when I go into that darn pantry, there's 2 Ho-Hos and a Kit Kat, I'm happy, right? I don't care if there's 8,000 Ho-Hos and 17 Kit Kats. I don't care if there's, I don't care the ratio. As long as when I go into that soil, when I go into that pantry, there's enough there to satisfy my demand. So we have to think about plant requirements in terms of what type of demand the plant has for that nutrient, and is there enough in that soil, is there enough in that pantry to satisfy that demand? So for example, this is research that was done by Wayne Cousteau at University of Wisconsin in the late 90s, where he went out to prove that, where they had different fertilizer rates over the Kentucky bluegrass lawn for a whole year. So one of the treatments got 4 pounds of N, no pounds of phosphorus, no pounds of potassium. The other treatment got 4 pounds of N, 1 pound of phosphorus, no pounds of potassium. This treatment got 4 pounds of N, 3 pounds of potassium, and then we had a complete treatment. And then every month when he'd do his clippings, he would look at how much nitrogen, phosphorus, and potassium was in the leaves. And what did he find? There was 0 differences statistically. There was no differences. So even though he put down a bunch of phosphorus and potassium, he had same levels of phosphorus and potassium as he did in every other treatment. Well, why is this? It's because the soil already supplied the plant's demand for those nutrients. The soil at the start already had 62 part per million phosphorus and 180 part per million potassium. It didn't need any more phosphorus or potassium to be satisfied. So we put more down. The bank account got fuller. Over time, the treatments that got phosphorus ended up having higher phosphorus levels than the one that didn't get phosphorus. But we didn't see a plant response because the plant was already satisfied for that nutrient. So then why do we soil test? Ultimately, the old school way we do it is to try to figure out, do I have enough of these nutrients? And I'm going to tell you, that's kind of a crappy way to soil test. That's not why I soil test. I don't soil test really to know what is the number, how much is there. It's good to know, but what I really want to focus on is how is that number changing with time? So if we go back to the bank account analogy, everybody in this room has a different number for how much money they want to have in their bank account at all times. All right? Millennials like me, we have no problem spending it down to nothing, knowing that we're going to get paid on Friday. Right? Then there's other people that say, I need to have 10 or 20 grand in the bank because maybe I'm a federal worker and I don't have any money to pay my mortgage for a couple months, right? So you build in some safety factors based on what you are trying to protect yourself from. So if I'm monitoring my soil, I want to see, are my numbers going up? Are they going down? Are they staying the same? And then ultimately, you just kind of figure out what numbers are appropriate for you. Some people here want their numbers to be really low. And they're okay with that. Some people want to have high levels of, say, phosphorus. And that's fine, too. Just find a number that you're comfortable with, that you think your grass is happy with, it's satisfied for its demand with, and then try to manage to stay in that range so it's not going up or down. We can also use it for diagnosing problems. If you got an area that looks bad, an area that looks good, you soil test this area that's bad, that area is good. Are there differences there? That's one way we can soil test. And then we get a lot of peace of mind out of it. We just know a little bit more about what's going on. You're not guessing. All right, so if we're going to do this, we're going to do it right. We got to, do proper sampling. The most important part is we have to select the proper tests, and then we have to figure out, what do those numbers mean that come from the test? So sampling is pretty straightforward. We sample representative areas. We sample areas that, you're going to manage the same. If you're not going to manage this part of the field differently than that part of the field, then it probably doesn't make a lot of sense to sample those areas independently. Or if you say, this area already has low nutrient levels, maybe you just sample that spot and you just treat, the whole field based on the area that you know is maybe the problematic area. I mean, those are things you can do. How deep? It's important. Don't just go jacking around, just, I got 2 inches here and 4 inches there and 6 inches there. This is an example why. I did 3 soil cores from a sand-based putting green, it could be a field, 0 to 1 inch depth. My soil test phosphorus, 200 part per million. I go to the right next to that hole, do a 2 inch depth. I get 138 parts per million. Right next to that hole, 6 inch depth, 74 part per million. Why is this happening? Well, the roots are constantly mining nutrients, right? And what are they doing with those nutrients? They bring them up to the top where the grass is growing. And so we start to accumulate more nutrient up at the top. So if you want to figure out, do you have enough of a nutrient, or more importantly, are your nutrient levels changing between, year to year to year to year, you have to have the same sampling depth. For example, if the first year you sample at 2 inch depth, and then the next year you sample at a 1 inch depth, you'd be like, whoa, I put way too much phosphorus down last year. No, you just sampled at a wrong depth. Or if last year you did 2 inches and next year you do 6 inches, and you go from 138 to 74, you go, wow, that's a huge drop. I need to put more phosphorus down next year to slow that decline, okay? So if you're going to do this, we really like the 4 inch depth, kind of for everything. 6 inches are generally more for lawns, native soils, but any high-performance turf areas, even if there's some native soil there, we like the 4 inch number. And one of the reasons is the interpretation. The ability for me to say is it low, medium, or high is generally done with 4 inch sampling. So that is important. So we got our sample. We got a lab we're going to choose. We're going to send it off. What's going to happen next? We're going to dry that sample. We're going to grind it up. Then we're going to add this chemical extractant. Usually it's an acid, maybe some ammonium, some fluoride, try to break the phosphorus off. We're going to shake it, and then we're going to just count the number of elements that are in that extractant solution. So there's different ones out there. There's a water one or a weak salt. Don't like this one because it measures what's in the soil solution, and it only gets some of what's on the cation exchange sites. So that'd be like assessing your wealth by only looking at your wallet. So I'd be, dead broke because I never have cash, right? So that would be a saturated paste or a water extract. Then people would do an ammonium extract, and that extracts the nutrients that are on the cation exchange sites, and it's in the soil solution or in your wallet, but it ignores phosphorus because it can't break that chemical bond. So the most popular tests for soil testing are things like the Morgan, the Bray, the Malick, the Olson. We really like the Malick. Don't let people tell you can't use the Malick in high pH soils. It's wrong. You can. Okay? It is a pH insensitive soil test from ranges from 5 all the way up to 7.5 to 8. If you're well above 8 and you have a lot of maybe sodium chemistry going on, an Olson might be a better extractant for you. But for most people in here, if you're between 5 and 8, the Malick is the best test. And the reason I say it's the best test is we have the best interpretations for what those numbers mean. And so that's why we like that test. So you tell me you have your soil. I'm going to come put my Malick 3. So if you're going to go soil test, ask for it. Because they might not give it to you right away. Say, I need the Malick 3. They might say it's $5 more. Well, it's worth it. Otherwise, you're using a test that you don't even know what the numbers mean. So why even doing it, right? So do the Malick 3. You take your soil. You got the soil here. You have some nutrients floating around in the soil solution. You got a bunch of nutrients bound up to the soil. The extractant comes in. It displaces all those nutrients. Now we take that extractant, we put it into a machine, and we analyze it, and we just count how many calciums, how many magnesiums, how many potassiums, how many phosphorus molecules are there. So that is the result. So if you are trying to figure out, what's the important numbers to look for, you want to look at your results section. Because those are the numbers, that's the bank balance. How much money is in each account. And you think about each nutrient as like its own separate account. Is the phosphorus account high? Is it low? Is it medium? And again, that number, I could give you some rough guidance on what that means with interpretation, but figure out what it means to you so that you can kind of say, this is, where I would like to be. If you're going to do sampling, again, be consistent so you can monitor how are things changing over time. Use the same lab. Use the same tests. Use the same areas. Ask what kind of tests. Know these questions. Too often, people give me a soil test report, and I say, well, what extractant did you use? No idea. I know Malic is a really weird name. Sorry, too bad some guy named Jones couldn't have invented it, because a Jones 3 is a lot easier than Malic 3. But hopefully it's weird enough that you can remember, like that M1, the Malic one, the M thing. That's the one you want to ask for. All right, so now we get these numbers, and we get to figure out how are we going to manage based on what the numbers are telling us. So here's a soil test report that comes from University of Wisconsin, and it's really straightforward, and it's really simple, and it doesn't have that many numbers on it, right? I got my pH, my phosphorus, my potassium. Down here's my results. I have my number, pH 5.9, phosphorus is 10, potassium is 34, organic matter is 2, 1.9. Okay? The question is 10 part per million phosphorus, is that low? Is that medium? Is it high? Is it ideal? Do I need more? Do I need less? And so on their report here, they'd say that's a low. And the pH is in the medium, and the potassium is also in the low to almost into the medium. But where do they get that number from? Right? How do they know this? Other reports have a lot more figures on there, and they're saying things like your zinc is low, or your copper is low, or your boron is low. Where do they know that there's a boron deficiency going on at that level? And I'll tell you, as someone that studies soil fertility, there's not a lot of good research to even tell us that this level of boron is too low for turf. So where do these numbers come from? They come from other crops like wheat or corn or even plants like soybeans. And they just said, okay, that works for corn, I'm just going to give it to the turf and say that works for turf. So there's three ways that people can kind of figure out what those numbers mean. One is the university recommended way, and that's called the sufficiency level of available nutrients. It's good. It's got its drawbacks. It's the best that we have. And I think the thing about it is I'm not selling you anything. So why would there's no motivation for me to try to manipulate this to say, these numbers are what you need to be at. Then there's another method called base cation saturation ratio that's developed by Rutgers University, but over the last 90 years has been consistently shown to not be very efficient. And then in the turf industry, we have this minimum level of sustainable nutrition, MLSN. Pace Turf and Micah Woods at Asian Turf Center have been kind of pushing that. And it's helpful, but the numbers aren't dead set hard numbers. And I'll explain what that means in a second. So let's talk about the university recommended way. So if we wanted to figure out, say, how much potassium needs to be in the soil, so soil potassium in pounds per acre, and then I'm looking at things like corn yield, I can then say, all right, as I'm increasing the potassium in my soil, higher and higher and higher, my yield is going up, 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 and then it stops. So if you're a farmer, how much potassium would you want to put down? 300 would be ideal for maximizing yield, but for the most part, they actually even go a little lower because farmers really want to make money. They don't really care how big their yield is. And so to go from, say, 200 to 300 might take a lot more fertilizer for a very small amount of yield, right? So that's your economic potential threshold there. Anyways, what we'll do then is we'll kind of then say, all right, anything in this pool we'll say is low. We'll say anything in this pool is medium. Anything in this pool we'll say is optimum or high. All right? But again, human hands had to be involved in that. Someone might say, well, I'm just going to say 1 to 25 is low, and 50 to 150 is medium, and anything over 250 is high, right? So there's some leeway in there. So you have to kind of figure out what is the rule that you said that differentiates between low and medium. But we can do this for anything. We can do it for phosphorus, calcium, magnesium, pH. But we can only do it if we see a response, right? If my calcium ranged from 1 to 400 and the bushels of corn were the same the entire time, you can't say how much calcium is really required there. You'd say that calcium may never need to be required, but those are some of the things. You have to have some kind of a response. And in turf, what is that response? It's quality, right? Bushels are easy. I can count those. Quality is a lot harder. What does the grass look like? Well, your idea of what looks good is probably different than what your idea of what looks good. So that can be a challenge. So here's an example of doing university research for calibrating soil tests for phosphorus. So this is my master's research. USGA putting green, it's 100% sand-based, no peat in there. This is bent grass, obviously. Straight sand, for your reference, is 3 part per million malic 3 phosphorus. Okay, so when it comes in from the quarry, that's what we're getting, 2 to 3 part per million. Most textbooks would say you need to be over 50. So you have kind of where we would want to be, where we're starting out. So we can see these grasses here, they look deficient in, or they actually look like they're wilting. And this is the same thing you'd see in ryegrass and bluegrass. They have this purple, sunken color, slow growing, look like wilt. You stick your moisture meter in the ground, they're wet. You're like, is it a root issue? What the heck's going on here? And you ultimately come and you soil test. And you find that they started out, these sands are essentially right at about pure sand. 3-4 part per million malic 3. Really, really low. So again, the ideal number would be 50s, according to a textbook. So you'd expect this one to maybe be like 50. Well, how about these? These look a little bit better. How high do you think they are? Oh, they're only 5. So we're still way below 50. How about 6? I don't have any 6s. But I had some 7s, and those look great. And over 7, didn't matter. Why? Because the plant's demand for phosphorus is satisfied at 7. If it had 85 or 8,000, it doesn't matter. It only needs 7. It went into that pantry and said, I need 7 ho-hos. You got it? Yeah, cool. I'm okay. I'm satisfied. All right? So this is what our critical point would be. But the problem is, this is on creeping bentgrass in Madison, Wisconsin, on their climate, in this soil, right, and then under this level of nitrogen fertilizer. If I fertilize more aggressively, say I doubled my fertilizer, or nitrogen fertilizer, maybe the number then starts to become 10, 11. Why? Because that grass is growing faster, and it needs more phosphorus to satisfy that increase in growth rate. So the more N I put down, the more phosphorus I need. So what I have to do as a researcher is then say, well, I'm in science, and I can't give you hard numbers on anything, so let's just multiply that 7 by maybe 3, and say if you're at 21, you're probably pretty good for phosphorus. Still lower than the textbook, but again, where'd that come from? It came from corn. It didn't come from turf. This is one of the first malic 3 calibration studies in turf, and we found it to be 7. So there's some limitations there, but it gives us a good kind of idea of where we're at. Then there's this base cation saturation ratio. This model says, let's look at just the cations. So this is only for phosphorus. And we can do the same type of thing for potassium, and it's okay. It's not great. Harder to do. We can do it for other nutrients, and we can't even do it. Why? Because we can't get deficiency symptoms in the field to even, tell us that where this break point is. So I can't get soils in the field to have low enough calcium in which I ever see a reduction in quality or growth rate as a result of not enough calcium. So I can't possibly even give you a number for what too low of calcium is. So let's focus on a different way of thinking about cations like calcium. And this idea was, if we had an ideal ratio of just the cations, calcium, magnesium, potassium, acidity, maybe sodium, if we had this ideal range that we're going to maximize the plant's health. The flaw with this is it assumes that the plant is not selective for nutrients. So we're going to total up the amount of charges of calcium, magnesium, potassium, hydrogen. We're going to total those all up. And so in an ideal soil, based on this research from Rutgers 100 years ago on sand pine barrens, was that we wanted to have 65 to 85% calcium, 6 to 12% magnesium, 2 to 5% potassium, and the rest should be either ammonium or acidity. But it's been tested now in turf and tons of other crops, and it doesn't work for several reasons. One, it ignores the plant. If I go back to my pantry analogy, I don't care if I want 2 ho-hos and a Kit Kat, if I have 50,000 ho-hos and 4 Kit Kats. It doesn't matter, because everything is independent for each other. The plant knows how much calcium it wants, it knows how much potassium it wants. It doesn't matter what the ratio is. It just wants to know, if I go in and I want 2, are there 2 in there for me to take? The other problem is, it assumes uniform nutrient distributions. How are you going to fix a calcium deficiency 6-inch depth? You can't, right? So that's going to be a problem. And we do know that how deep we sample, we're going to get different percentages. We know there's a ton of soils that can support great growth despite having this ideal magical range. And so ultimately, it's just really inefficient. We're putting down products to solve problems that are imaginary. They're not even real. And so those are things that we'll see on this base cation saturation ratio. Let me say, though, the one thing that we do pay attention for on this is if you have sodium and you have clay or native soils. Because when you get a lot of sodium in those soils, so if you have people with salt-affected soils, specifically with sodium, we do look at the percentage of sodium to the other cations. Because when you start getting more and more sodium, it starts to relieve the soil structure. We'll talk about that towards the end of today. But anyways, for the most part, they'll take all these formulations and we'll just make these ridiculous figures. It's another thing I just found on Google. Just look at all of the things that are being interpreted here as a result of just measuring the quantities of just a couple of nutrients. And for the most part, we don't know what any of this means. So finally, the other way of interpreting is this MLSN concept. And so it's developed again by Pace and Asian Turf Center. They have way more than 3,700 samples now. And the idea is like this. I went to the doctor for a physical last week, and he did my blood pressure, and I was 120/70. Okay? What's the ideal blood pressure? 120/80, 120/60 out here. Where do they get that number from? Right? Some doctor's not going to go in there and jack up someone's blood pressure and be like, let's see what happens to you, right? That's the university way of doing it. I'm going to sit there and I'm going to purposely make someone's blood pressure be really high and watch if they die or not, right? So they're not going to do that. So we can't do these same things that we would do for, that's what we're doing here with this. We're manipulating the system. If this grass dies, ha ha ha, great, We can't do that with human health. So they take that same concept with soil sampling. So they're going to take thousands and thousands and thousands of soil samples. And when the samples come in, they're going to look at only sand-based soils, Malic 3 results from a pH of 5.5 to 8.5. Low CEC, again, means it's a sandy soil. So when I see a number of that, I just know it's a sand. And they're going to say, okay, if I have all these samples and all the turf managers are saying the grass is healthy, then, about what are they doing? The same thing that doctors do. The doctors take all these people, 20, 30,000 people's blood pressure, and they say people that are in this group that are pretty healthy, averaging somewhere around 120/60, 120/80, right? And people that are maybe 200/100 or something, we start to have all these problems we start to observe. So that's that same concept that's going to happen here. We have all these samples that are performing well, so if we ignore the ones that are performing poorly and just look at the ones that are performing well, what range are we at? So here's an example of the data that they generated for, say, potassium. The textbook would say that the soil should have 100 part per million potassium. In sands, that might not even be achievable. You probably can't even get 100 part per million potassium in sand because it doesn't hold that much nutrient. So you're just constantly putting it down, and your soil test report keeps saying low potassium, low potassium. So all of these people that submitted samples are therefore saying that the textbook would say that they are deficient. Well, how could that be? Because all these thousands of people said, actually, my grass is performing really well. I like it. I just soil tested to see where I was at. So what does that mean? It means the textbook's wrong. It doesn't mean the people are wrong. The grass is performing well, then great. So what they're going to do is they're going to look at, okay, well, how low can we get in the soil before we stop getting these reports of the grass is performing well? So we can see, our 100s, 90s, 80s, 50s, 40s, 30s, 20s, 15. I'm not getting a lot of samples way down here. So maybe this is kind of where I want to have my cutoff. And maybe I don't want to go all the way to the edge. So I'm going to draw a line so that 90% of the dots are on this side and 10% of the dots are on that side. And I'm going to say that's my critical level. But again, that's where the human interpretation comes in. They chose 90% on this side, 10% on that side. If they would have chose, say, 5%, then the line would move even further this way. If they would have chose 15%, the line moves that way. So use MLSN not as a hard number. Use it as a guide to say, okay, where am I relative to the crowd, right? I'm kind of in the middle with the rest of the people, or I'm a little bit on the low side, or I'm kind of high. And then you can use it to figure out what number you want to stay at. So here's an example of that for, say, potassium. They'll look at, the distribution of samples that come in, looking at how it ranged, and they'll drop their line at, say, 10%, and they'll say, okay, if you're at 37 part per million, only 10% of our samples that are called good and healthy are less than 37, and 90% are more than 37. So that's where they got 37. Again, if they would have used 15, then they would have moved there, and they would have said 40 is the line. Okay, again, it's not a hard number. It's just giving you reference to the rest of the population. Phosphorus, same thing. If they would have did, say, 60%, their number would be 50. But if instead they did 10%, so the number they got was 21, which is exactly the same number that I found in all my university research, which is just ironic. It doesn't mean it's right. It just means that, maybe around 20 part per million is kind of a good goal to stay around. So that's one way of looking at MLSN, is to just kind of, where are you relative to the crowd? It's not a hard number. It's just a way to give you reference to what your soil samples actually mean. All right. Let me get some drink of water here. Any questions so far about that? So we kind of covered those three pretty quickly, but they're pretty important parts of this. All right, either I did a good job or I suck and you're boring. And it's boring. It's cool. All right, so how do I do it? First, I would be consistent. Because, again, I want to use my soil test reports as kind of looking at my bank statement from month to month and not worry. So there's going to be months where the bank's kind of low. There's going to be months where the bank's kind of high. As long as I'm not, I can still buy groceries and gas, I'm still happy. And so I want to be consistent so that I'm having, similar numbers to compare against. So I would do it every year. Honestly, people like to do it every 3 years. In the golf world, people do 6 greens 1 year, 6 greens. I hate that method. That's stupid. Just find the green that's got like the highest nutrients, the lowest nutrients, and the middle nutrients, test those. So if you have multiple fields, you test one field that's the high one, you do the low one, you do the middle one. If you got one field, just do one sample a year from your field to kind of get an idea of what's going on there. I do it in the spring. Why? Well, start the growing season off on the right foot. Know what's there going into the season. And then also, if we had snow melt or rainfall, I want to see how did that change over the winter time when the plant wasn't taking nutrients up. Representative areas, again, I like 4-inch depth. I use the same accredited lab that I know and trust. But the most important thing is I always ask for this Malic 3. That's the one thing. If you leave here today, please ask for that test. Unless your pHs are well above 8, then you'd probably go with an Olsen. And by doing this, I can now monitor how things are changing over time. So what nutrients do I really even care about? Or what things do I care about? Well, I care about phosphorus because we have good phosphorus response data. I care about organic matter, not because there's a hard number. Rakaswaz, my counterpart, he does a ton of research on organic matter accumulation in sand-based soils. And he'll say, I can't tell you a number. But you can see, is that number going up, down, or staying the same? So again, you might say, well, my fields perform well when I have 3%. If it's 1%, maybe they're too thin, they're not stable enough. If it's 5%, I'm getting thatchy. So now you can start manipulating not your fertility, or you can manipulate your nitrogen fertilizer, because that's kind of an impact, but also your cultivation. Are you over-aerating, you're under-aerating, you're over-top dressing, under-top dressing? That's an important one. Potassium, we have some good data on, but I was telling you before, potassium is kind of a challenge because a lot of our sands, especially in the eastern half of the U.S., but can have potassium in the sand. And that sand can actually start to break down and release just low amounts over the year, and that could even add a feed. So sometimes our sand can even act as a fertilizer. But we can get kind of rough numbers. pH is just kind of a good idea for micronutrient deficiencies. If you know you have high pHs and you have Kentucky bluegrass, for example, and you get a chlorosis there, you might do foliar applications of micronutrients because you may have problems with it. You probably can't change your pH, which is good to know. And if you deal with salt, you're down here in the Southwest, we're going to look at our electrical conductivity or how the salt level is in the soil. And then also, we're going to look at our exchangeable soil percentage. This is the only cation ratio that I care about. When it starts getting above 5, then I'm going to be concerned. But I'm only going to be concerned if I have native soil. So this is called Sodicity, if it's above that. So when soils have high levels of sodium relative to calcium and magnesium, they start to lose their structure, and so water doesn't drain through them quickly. So the large pores that drain water away and let air get down to the roots get smaller. the continuity or how the pores are connected starts to fall apart. So that our drainage rate starts to reduce, our soil becomes harder, and we get less oxygen to sustain our roots. But again, this only happens if you have soils with structure. Those are native soils with silt and clay. So here's our silt and clay. We can see the different particles are kind of bound together. So we have some big channels here that can let air and water in, and we have the small little pores, the micropores, that will hold on to that water to feed our plant. So if we have a bunch of sodium there, it causes the clay particles to kind of lose their stickiness, and they start to clump together like talcum powder. All right? And then there's no big pores. So there's a lot of little pores that holds water, but there's not ways to drain water or get oxygen there. And so by applying calcium in these situations, only when your exchangeable sodium percentage is above 5% can be helpful, but only in native soils. Sand doesn't have structure. I don't care if your sand is 20% sodium. It's not going to have an impact on it. It's not. You don't need to put calcium to displace a problem that doesn't exist because you don't have clays to disperse. You're fixing a problem that doesn't occur in sand. So don't worry about it. If your salt levels are high, you have a bunch of sodium, it has causing your salinity to come up, that can be a problem, but how do you fix salinity issues? You leach, right? You don't add more calcium, which is a salt. You don't add a salt to fix a salt. You only put the sodium down if you're having issues with native soil and you start to get those exchangeable sodium percentages up above 5%. Okay? Same thing with carbonates. I'm just going to throw it out there right now. Carbonate levels are problems in native soils. So you do your water testing, you get high carbonates, you got native soils, maybe a concern, especially in dry climates where a lot of water is applied, not much leaching is happening. We've tried to make calcium carbonate issues in sand soils. We can't do it because the pores are so big that we don't see them clogging up that pore space. People will say, well, I can see it on top. And you see that white crust. The white crust is forming on top of dead algae, and as the water evaporates, you see that white calcium on top of algae. And we think it's the calcium. No, it's algae problems. It's not from the calcium. And that's been researched now for 5 years, and we've been trying in labs and in the field to make it happen. We can't make it happen. So then we get down to the talking head part of soil testing, and then this is what we need to do based on my interpretation. So I'll end here. And the thing to really realize is that nitrogen fertilizer is obviously the most important thing that we manage as turf managers, and we all know that. But do you know that clipping yield response, your growth rate, will continue to increase in cool season and probably in warm season grass, see what we haven't tested it there, up to 16 to 20 pounds of N a year? So if I'm at 14 pounds and put another pound down, I'm going to see a further increase in growth rate. And so by increasing growth rate, I'm increasing demand for all those nutrients. The plant's demand for nutrients is increasing as growth increases. So clipping yield is going up. What's also happening? Nitrogen uptake is going up. Potassium uptake is going up. Phosphorus, calcium, every nutrient is needed at higher levels as you increase your fertility level. So when you think back to how much, say, potassium do I need or how much phosphorus do I need? Well, the example I had before was for a bentgrass putting green receiving a half a pound of N a year or a month. If I would have did a half of a pound every 2 weeks and it's growing double as fast, that number would probably go up. If the grass is growing slower, the number goes down. That's where I can't give you guys exact numbers, and you have to kind of figure out what number are you comfortable with. So referencing, say, MLSN, where are you relative to the crowd is going to be the helpful part. So a good way to think about this is to think about it not in terms of nutrient, say, is to think about is the nutrient ratio of, say, phosphorus to potassium, nitrogen to phosphorus, nitrogen to potassium. How are those numbers, how are those ratios changing? So this is some good research from Wayne Cousteau at Wisconsin, where he looked at athletic fields, sand base, bluegrass, clippings being removed. If you didn't want your soil test numbers to go up or down very much, for every 4 pounds of N, you'd want to put down 1 pound of phosphorus and 4 pounds of potassium. If you're returning clippings, then we're recycling nutrients, so then it'd be 8 pounds of phosphorus, or 8 pounds of nitrogen would put down 1 pound of phosphorus and 8 pounds of potassium. If I go to a native soil, my numbers go to 8 to 1 to 4 and 4 to 1 to 3. Why less potassium here? Because the sands leach potassium a lot more. So, there's going to be factors that are going to influence these numbers. For example, if you have a lot of rainfall, you might need more potassium. If you have a lot less rainfall, you might have less potassium per pound of nitrogen. But if you try to hit kind of roughly around these numbers, your soil test levels won't change. So for example, say I was going to my field and I put down 4 pounds of N last year and 2 pounds of phosphorus and 4 pounds potassium. What would happen to my soil test phosphorus level? Likely. If I use a 4 to 2 to 4 ratio, it would go up because I'm applying a little bit more than the plant would need. If I did a 4 to 0 to 4 ratio, the phosphorus probably goes down. So what that allows you to do is figure out if I'm getting close to with my goal area, maybe if I have a lot of phosphorus in my soil, maybe I don't use any phosphorus for a couple of years. And then I start to approach where I want my phosphorus to be. Then I start slowly adding phosphorus to my program. And I'm going to monitor, is the phosphorus level starting to stabilize or is it still going down? Is it still going down? Well, then I'm going to put a little bit more phosphorus down next year. And if it's going up a lot, then I put down too much. I'll put down less next year. Again, remember, nutrient deficiencies are not going to kill the turf right away. Okay? They're not going to kill the turf anyways. It's just going to be thin, maybe not as vigorous as it could be, but it's not like a disease. So how would I fertilize? How would I do this? Just kind of wrap everything up here. I would soil test in the spring, and I would just completely ignore the base cation saturation ratio. I would just, unless I had sodium issues, then I would think about it. But if it's my sand-based backyard putting green, I'm not worried about it. I'm going to use only nitrogen. Maybe nitrogen in a micronutrient package if you have high pH soil, like iron or manganese, things that you have issues with. But I'm going to use only nitrogen until my, say, phosphorus and potassium levels start to approach the MLS range. And so what I usually say is a good range would be if MLSN is 20 for phosphorus and 40 for potassium. If I'm somewhere between, say, 20 and 40 for phosphorus and 40 and 80 for potassium, I kind of want to stay in there. Because if I'm in that range, I'm kind of running with the pack. I'm not too high. I'm not too low. So I'm going to just kind of monitor my soil tests over time. Are they going lower and lower and lower? And then when I get into that range, what I'm going to try to do, I'm going to start totaling up every year. How much N did I apply? How much phosphorus did I apply? How much potassium did I apply last year? And then when I soil test in the spring, I'm going to say, did those numbers start to stabilize so that are in that reference range of 20 to 40 for phosphorus and 40 to 80 for potassium? Or do they go up, or do they go down? And then I'm going to tweak my fertility program so I can try to stay in that range. So then I'm going to apply my P. If for some reason I need to apply, I'm going to apply my P and K in the spring because I want to get my soils, where I need to be right away in the springtime. I don't want to wait. And, if I'm deficient in phosphorus, I don't want to be deficient until July application. So I'll make a corrective application in spring. And then I'll kind of guess where my N rate will be that year, and I might split up the rest of the app, especially the potassium, across that season to try to keep it where I want it to be. And then if I'm doing if I'm worried, I get a test result back, and it says my zinc levels are too low. And we know zinc can be an issue in, say, corn, so I'm not saying it couldn't ever be low. But just know that those numbers on soil test reports, they're not very good for turf. So if you think the zinc is low, get a zinc source, get this zinc sulfate, and if you can find that and dissolve it, or just get some of the products that contain zinc and apply it just a small area. If you don't see a response in a couple days to a couple weeks, you didn't have a zinc issue. I wouldn't worry about it. If you see a response, like the iron response that we saw in 2 days, you say, yeah, I have an iron deficiency. Let's go buy a bunch and go treat everything. Okay? If you want to treat just the field because you feel good about it because zinc's cheap, well, fine. But again, at least you have a spot you don't treat just to kind of see did that benefit or not. So everything I've talked about here can be found in this that we call NEB guides in Nebraska, and it's a Nebraska extension. You can sign up for these NEB guides, or you download them for free. I think you can pay for them, but you can download them for free, which is stupid. That's a university for you. So you just Google simplifying soil test interpretations for turf professionals. If you can't find it, just email me. I'll send it to you. And it talks about everything that I talked about today in an hour in just a couple-minute read. But the thing that's really helpful, I think, at least I hope it's helpful because I wrote it, at the back is, if it's not helpful, then I'm just really bad at my job. I have the back page of it. There's this like cheat sheet. So I have the nutrients that I'm caring about: phosphorus, organic matter, potassium, pH, salinity, and sodicity. Again, only for native soils. And then what would I do if my numbers are different? Notice for sodicity, though, this is going to be for bluegrasses for the most part and cool season grasses. So some of the grasses like seashore, paspalum, are going to be very different than you'd be dealing with for, say, a bluegrass. It's very sensitive to sodicity. And it then tells you, like, okay, if you're, what you should do, if it's low, medium, or high, but more importantly, like phosphorus. I think in a good, safe spot to be for all grasses growing, especially on sand-based fields, would be 25 to 50 part per million. If it's less than 25, what would I want to do? I'd want to apply more than a quarter pound of phosphorus for every pound of P or nitrogen I'm applying. So if I put down 4 pounds of N last year, maybe I put down 2 pounds of phosphorus, try to bring it up. If I'm in that range, then I'm going to try to maybe stay in that range, and so I don't want to apply too much or too little. I'll put down my 4 pounds of N, maybe down 1 pound of phosphorus, okay? And everybody's different. You might find that maybe your ratio is every 4 pounds of N, you only need to put down 3/4 of a pound. Or if your pH is high, maybe you got to put down 1.5 pounds of phosphorus. You'll figure that out by doing annual soil testing to see are your numbers going up or down. If it's greater than 50, I would say just don't even use any P yet. You're outside that range. Just save some money, do nitrogen fertilizer, do micronutrients if you need to, and just take that kind of an approach to it. Organic matter, there's not even hard numbers. So, if it's much greater, I can't even give you a number. If it's much greater than previous years, your organic matter, maybe reduce nitrogen fertilizer and water, increase cultivation and top dressing. If it's slightly increasing or the same, that's normal, especially for new fields. They're going to start accumulating a lot of organic matter in the first 10 years. After 10 to 15 years, we're going to kind of slow down. And then you're going to have, if it's less, well, maybe you're not fertilizing enough or you're over-cultivating. And so, again, you have to figure out, well, it's less, but it's still too high for what I want it to be, so I'm okay with that. So you have to, again, figure out what's appropriate for you. I have this free app called Greenkeeper. It's really made for golf courses in terms of like what it looks like. But all of the science that's in Greenkeeper, everything in here is applicable to sports turf managers too. And when you set up your golf course, you go into your My Course, you just select, I have the field. So you can pick like greens, tees, fairways, rough, or athletic fields. And so you can use Greenkeeper to do a lot of things for you, track different products, different pesticides. I do a lot of research on plant growth regulators and tracking how they perform. And we have all those models now for cool season athletic field turf in Greenkeeper. So if you want to know when to apply your Primo to your field, it's built in Greenkeeper. But it also can track our nutrients. So we can figure out, how much NPK did you apply? So if you're wondering what my ratios are like, I can say, okay, I've already put down 3.5 pounds of N, and I've only put down 0.8 pounds of phosphorus. Oh, good, I'm in that about 4-to-1 ratio that I want to be. So it's a nice, easy way to visualize that for you. But then we also have quick and affordable soil testing built right into it. We partner with a lab that's like all robotic, so they can turn things over really quick. And so you would go to your field and you just say, I want to make a new sample. You drop a pin on the field for maybe areas that you sampled. You print off a label. You send it into the lab. And then a couple days later, your results get put right in the Greenkeeper with all the interpretations we talked about today right there. I'm not overselling things. If you want to do this, do the basic test. There's a salt test if you got salty soils. There's a complete test because some people want to see everything, even though we don't even know what those numbers mean. They want to see them. You can pay more for it, but all I think you need to do is get the cheap $20 test, and then it's all in there. The best part, though, I think, is instead of having to hold all these stupid PDFs and look at them, all your reports year to year, your results are just graphed out. So, for example, my potassium in 2015 is going up, up, up. Why is that? I'm over-fertilizing with potassium. So then I stopped. It's going down. And so maybe I'm under-fertilizing with potassium. All right, so we can see your fertility change, and then you can reference back to how did you fertilize on those years to kind of get an idea of what's going on. So give it a shot. It's free. It's greenkeeperapp.com. University of Nebraska owns it, so it's a university tool.